If the Sun were to build a factory, its headquarters would likely stand in Kuka, Xinjiang. At dawn, the first ray of sunlight pierces the thin mist fringing the Taklimakan Desert. 700,000 PV panels track the sun, generating 600 million kilowatt-hours annually. Yet this power is not fed directly into the grid. Instead, it flows into rows of white workshops, where energy undergoes a complete transformation. Under the 14th Five-Year Plan, the Xinjiang Kuka Green Hydrogen Demonstration Project serves as a landmark for China's energy transition. It stands as the world's largest operational photovoltaic hydrogen production facility. A total of 52 China-made electrolyzers run non-stop to produce steady, clean hydrogen. Annual output is 20,000 metric tons, cutting CO2 emissions by over 480,000 metric tons. From blueprint to reality, from the Gobi to a hydrogen hub, this fully Chinese-designed, built, and operated green energy complex supports China's drive toward carbon peaking by 2030, with lasting clean energy momentum.
The vast Gobi stretches to the horizon. All of this is our treasure.
Song Chongbo is one of the designers of the Kuka project. He regularly pores over the project's operational data to monitor equipment status and accumulate experience for more ambitious, next-phase goals. The PV hydrogen production plant he helped design is the largest globally and redefines hydrogen itself. Hydrogen is not a new substance, having been utilized by humans for over a century. Conventional hydrogen production yields substantial carbon dioxide, hence labeled gray hydrogen.
Hydrogen from coal or natural gas is gray hydrogen. With carbon capture, the resulting hydrogen can be classified as blue hydrogen. Water electrolysis, however, produces hydrogen with zero CO2 emissions.
Green hydrogen earns its name for its zero-emission production. Renewable power electrolyzes water into hydrogen and oxygen, generating no carbon emissions. It seamlessly connects renewable power with hard-to-electrify industries, yet scaling up from gram-scale laboratory demonstrations to industrial production on a 10,000-ton scale once seemed an insurmountable technical barrier.
We were shocked when we received this task. Based on experience, water electrolysis consumes massive energy. Electrolysis was only used in small test or demonstration units, with output of dozens or hundreds of cubic meters. Building a 20,000-ton plant in Kuka is both a major breakthrough and a huge challenge for us.
Scaling lab setups into industrial production lines brings exponentially compounded difficulties. Beyond capacity expansion, the project brings greater complexity in materials, equipment, control, and system integration. The first major challenge facing Song Chongbo and his design team was identifying the heart of the world's largest green hydrogen plant, and they settled on the electrolyzer.
Normally, for our alkaline electrolyzer, when powered, hydrogen forms at the cathode and oxygen at the anode. Hydrogen and electrolyte flow via dedicated pipes to the hydrogen separation tank, while oxygen and electrolyte enter the oxygen tank to separate gas and liquid. This process is straightforward and mature.
As the heart of hydrogen production, electrolyzers turn electricity into chemical energy, splitting water molecules for continuous hydrogen output. However, an improper selection would severely destabilize the entire project system. Upon project initiation, Song Chongbo found himself at a crossroads between the two mainstream electrolysis technology pathways.
One is alkaline water electrolysis for hydrogen production. The other is PEM electrolysis. During project construction, our PM technology remained immature and had to be imported. The cost, however, was extremely high. By contrast, alkaline electrolysis is mature in China and far cheaper, but it responds more slowly to fluctuations in the power supply.
Photovoltaic power is weather-dependent and volatile. While foreign technologies offer fast response, they place this industry in foreign hands. Domestic technologies deliver full independence and offer cost advantages, but they face a global engineering challenge, responding slowly to fluctuations in the power supply.
For our project, we need both low costs and fast response speeds. At Sinopec, when picking equipment, we always opt for mature, reliable domestic units, built on our own technology. It's our standard practice.
This was more than a technical choice. It was about safeguarding China's ability to develop its green hydrogen industry independently. The team didn't hesitate. They chose the tough yet fundamental path for national energy security. But the harsh Gobi environment has only worsened. The Chinese alkaline electrolyzers, sluggish response.
Generally speaking, PV power naturally fluctuates all day with sunlight levels. It is inherently volatile. Extreme weather such as sandstorms mainly affects PV power generation.
Kuka's sunlight is abundant yet erratic. PV output peaks sharply at noon, and unresponsive electrolyzers will cause massive power waste. It drops steeply in morning and evening hours, and delayed system adjustments will trigger safety shutdowns and interrupt the hydrogen supply.
One thing about the PV output around Kuka is that it surges wildly within a single day, especially during bad weather or when clouds roll in. And our forecasting system just can't predict cloud cover or anything like that. Sinopec Tahi Refining and Chemical needs a stable hydrogen supply around the clock, making it hard to balance supply and demand.
As a major heavy crude processor, the plant has little tolerance for supply fluctuations. Nevertheless, frequent sandstorms and extreme diurnal sunlight shifts render PV power generation in the Gobi unstable, jeopardizing Taher's manufacturing operations. On one side, PV output fluctuates with the weather. On the other, the hydrogen supply cannot be interrupted. This mismatch exposes the slow response of alkaline electrolyzers, bringing the project to a standstill.
We operate one of the industry's major green hydrogen demonstration projects. Any minor safety hazard here will be massively magnified and may hinder the sector's growth.
Safety risks are a critical concern. In alkaline electrolyzers, H2 and O2 are separated only by a thin alkaline liquid seal, which requires precise dynamic pressure balance to function. Severe power fluctuations can easily disrupt this balance and trigger cross-mixing of the two.
This is hydrogen production's top safety risk. Hydrogen has a wide explosion range. Hydrogen concentrations from 4% to 75% are explosive. If hydrogen and oxygen mix, there's a huge risk of explosion.
How can the slow-reacting alkaline core keep pace with the erratic swings of power supply, while guaranteeing robust, steady and safe operation? It was at this juncture that Song's team turned their attention to an intelligent solution integrating flexible buffering and AI. They equipped this massive plant with a high-capacity hydrogen storage buffer as its flexible lung, and added an AI brain able to sense, decide, and control.
Actually, this is just our preliminary plan for now. Our intelligent control system is the core. Look, we've got around 60 to 70 units that can adjust hydrogen output in real time to match PV fluctuations. When solar power is available, they adjust hydrogen output to make full use of it. When solar generation drops off, we draw hydrogen from storage and send it to Taher via compressors. So we need a custom intelligent control system.
The team jointly devised an integrated scheme, combining hydrogen storage and intelligent control. They paired their own systems with Chinese green hydrogen production technologies, equipping the hydrogen plant with an AI brain. This ensures autonomous load adjustment, safety monitoring, and overall operational stability. To address key safety risks, the team simulated extreme operating conditions, refined every technical parameter, and iteratively revised the drawings. When the system went live, and successfully handled its first sudden PV power drop, the whole team sighed with relief.
We all felt anxious about the reliability of the process. Before making hydrogen as this was its debut deployment, once smart control took over, green electricity began flowing into the electrolyzers to make green hydrogen, and we were so excited.
Built on the Gobi Desert, this project breaks foreign tech monopolies and elevates China's hydrogen industry from follower to leader.
Since our green hydrogen project went live, many people came to visit, especially from overseas. One moment stuck with me. That time our plant was in operation, so they couldn't go inside. They crowded by the door just to watch our equipment. I felt so proud right then. It hit me that we'd pulled ahead technologically. Our homegrown equipment has entered overseas markets and continues to lead the industry.
With no experience, standards, or precedents to draw on, Song's team overcame the three major challenges of technology, the environment, and safety. They remained committed to a domestic solution and achieved a breakthrough in Chinese engineering. The project opened a new path to green, low-carbon development, and demonstrated the Chinese team's courage to venture into the unknown and innovate.
We originally planned 20 tanks. Then we reduced the number to 10. After comparing capacity and cost, with a capacity of 2,000 cubic meters, it is China's largest spherical tank. No larger ones have been built yet.
After Song's team finalized their master plan, an even tougher campaign unfolded across the boundless Gobi. Project manager Cao Yang is a veteran builder with nearly 30 years of experience in steel construction. He took on more than construction drawings. It was a weighty mission. Within 1 year, his team built an unprecedented, benchmark green energy facility, deep in the windswept Gobi, where gales rage year-round.
We faced huge pressure. The project had a total investment of 3 billion yuan. Sinopec aims to become a world-class clean energy company, and the pressure is on us to make that vision a reality. Tight schedules weighed heavily on us the entire time.
Challenges emerged from the very start. As a complex cross-industry system, the project comprises a PV station covering nearly 10,000 mu, 26 kilometers of power transmission lines, and a modern hydrogen plant fitted with 52 large electrolyzers. To the construction-focused team of Cao, photovoltaic facilities and large-scale green hydrogen systems are brand new domains.
I'd only seen hydrogen facilities at refineries, which are different scenarios. I barely knew anything about water electrolysis for hydrogen production back then. This was my first power engineering job. PV plants, flood barriers, and power lines. Electrolytic hydrogen production, circulating water plants, water treatment stations, and tank farms all fall within petrochemical engineering. The project spans a wide range of disciplines.
The first challenge was a shortage of core equipment. The project urgently needed 52 of China's largest alkaline electrolyzers. At the time, industrial production of large alkaline electrolyzers in China was still in its infancy, and no single supplier could handle such a large and urgent order on its own.
No single supplier could deliver all units. We split the order among 3 suppliers. Their electrolyzers varied in size and utility requirements, halting the design of all 7 workshops for more than a month.
Time was pressing. Rather than wait passively for suppliers to coordinate, Cao and his team leveraged their rich experience to put forward an innovative plan. Modularize functions and standardize interfaces. Cao divided the complex electrolyzer systems into standardized functional modules, breaking the design deadlock. All 52 electrolyzers were prefabricated as standardized module packages and assembled on site like giant building blocks, greatly improving efficiency and precision. Yet harsh natural conditions brought greater difficulties than the drawings predicted.
Our site lies in a Tian Shan mountain wind corridor, where weather shifts rapidly and erratically. Bright, cloudless weather could suddenly give way to heavy wind or dark clouds, bringing rain or hail. From April to May, sandstorms swept through every 2 to 3 days, leaving the air in persistent dust. Heavy sandstorms can sharply reduce weld acceptance rates and affect weld formation.
Faced with harsh natural conditions, Cao's team demonstrated the resourcefulness and perseverance of Chinese builders. They installed windbreak and dust suppression screens and mobile dust-controlled shelters for critical welding work. When sandstorms struck, all staff retreated to safe shelters. Once winds eased, even before the sky fully cleared, workers wearing goggles and face masks rushed back to their posts.
At peak construction, the hydrogen and photovoltaic plants each employed about 1,500 workers, managers, and laborers all lived on the Gobi. When sandstorms rolled in, walking outdoors meant sharp grit and flying pebbles stinging our faces badly. Unhelmeted workers would easily get head bumps from flying stones.
This was an unprecedented all-hands construction effort. Installation crews precisely laid photovoltaic panels across the vast Gobi. Workers erected transmission towers and laid cables along rugged terrain. Equipment hoisting, pipeline welding, and instrument testing ran concurrently in the plant. As chief commander, Cao covered tens of thousands of steps daily to oversee all sites. On June 30, 2023, the final PV subarray went online. When green electricity surged into the hydrogen plant and produced its first cubic meter of pure green hydrogen, the entire Gobi came alive. The milestone was completed 6 months ahead of schedule. Comparable projects overseas typically take 3 to 5 years to build. Kuka took just 17 months, a display of China speed, and a remarkable feat in global green hydrogen construction.
On the day the PV plant reached full capacity and began supplying power for green hydrogen production, we held a small ceremony there. Honestly, I felt no overwhelming excitement, only relief that we had fulfilled our mission. That's the grit and sense of responsibility all of us petrochemical practitioners live by.
The project now produces 20,000 metric tons of green hydrogen a year, reducing CO2 emissions by 485,000 metric tons. It sets a global benchmark for large green hydrogen projects and boosts exports of Chinese equipment.
Log the workshop's 7 differential level interlock and ask field operators to inspect the site. Depressurize and nitrogen purge the system. Notify fire control to inspect on site.
As commands were issued, a simulated hydrogen leak was safely resolved. Though merely a regular emergency drill, Chen Xingyu remained fully focused. As the operations manager, he keeps hundreds of thousands of PV panels,
52 electrolyzers, and an extensive pipeline network, running safely, steadily, and economically for decades, amid the harsh and volatile environment of the Gobi Desert. I was one of the first to come to Kuka in 2021 to handle prep work when our group launched this project. I was really excited. When I heard Sinopec was developing a green hydrogen project, to me green hydrogen will be a key clean energy fuel going forward, and it's important for keeping our country's energy supply secure. I'm so proud to be working here on this groundbreaking project.
What lies before Chen Xingyu is a complex dynamic system integrating natural, mechanical, electrical, and chemical variables, with severe natural conditions as its primary risk.
We had terrible weather once. Sudden clouds and sandstorms. As a result, our solar power dropped sharply, from 260 megawatts to 40 megawatts, making it really hard to keep steady production.
At the time, There was not a single company anywhere in the world that had proven experience producing hydrogen steadily, from variable PV power. Chen and his team had no model to follow. Only volatile weather and equipment that could not stop running.
Our PV power station covers roughly 10,000 mu, over 1,000 football fields. Right now its power generation curve looks like a parabola. But there's an issue we're facing. Sudden sandstorms drastically reduce its power output, which creates a major challenge for the stable production of green hydrogen, so we need to work together to tackle our current problem.
To align production load with PV power fluctuations, the team initially proposed partial electrolyzer shutdowns. However, Chen soon realized that this would be a self-defeating stopgap.
It is just like a light bulb, switching it on and off over and over again will make the bulb wear out much faster. Electrolyzers are no different. Frequent starts and stops also reduce their service life.
Yet inspiration often springs from casual moments in daily life. While cleaning his fish tank and observing pipe flow and water level fluctuations, Chen suddenly grasped the solution.
Think of the pool filling and draining problem from primary school. Water flows in at one end and out at the other. Think of this kettle as the PV plant, this container as the hydrogen production unit, this one as the hydrogen storage tank, and this as the hydrogen consuming unit. When solar power is strong, we produce green hydrogen via electrolyzers and store it in the tanks. If solar generation drops sharply, we'll cut the electrolyzer's operating load accordingly. Therefore, striking a balance among these four is the core of economic and efficient operation.
To align all operational links, Chen's team gathered massive operational data. Thousands of data sensors were deployed across the PV plant site. Real operational data was used to iteratively train and refine control algorithms. The system evolved from passive response to proactive prediction and adaptive coordination. The cloudy weather Chen had anticipated arrived as expected.
Whenever extreme weather disrupts solar generation, the system matches production load to PV output within 3 seconds and reduces hydrogen output to the preset level. And once solar generation bounces back up, we ramp hydrogen production right back to the matching capacity. I felt so excited back then.
The intelligent operating system of the KUKA project has run stably for over 900 days, with a load tracking success rate above 99.9%. It reliably copes with sandstorms and efficiently captures weak morning and evening irradiance. Even at 20% rated power, the system sustains efficient, secure operation to maximize solar energy conversion into green hydrogen.
Our intelligent production scheduling system can adapt to any green hydrogen demonstration project. It has been tested in Xinjiang's extreme weather, so we believe the system can be replicated anywhere in the world.
The system's design philosophy and core modules are now being exported along with China's green hydrogen technology, providing vital operating know-how for green hydrogen projects around the world. In KUKA, the sun produces more than hydrogen. It also nurtures Chinese ingenuity that lights the way to a greener future worldwide.
Our project has achieved large-scale green hydrogen production and large-scale downstream use of green hydrogen for the industry. It is a groundbreaking project with significant value as a pilot.
From Song Chongbo, who solved on the drawing board the global challenge of matching fluctuating power supply with stable demand, to Cao Yong, whose modular construction amid sandstorms delivered China speed that amazed the world, and Chen Xingyu, who used AI to maintain stable operations in extreme weather. On this Gobi, once filled only with howling winds, Chinese ingenuity has brought about an epoch-making energy transition. Age-old sunlight converges with the energy of tomorrow in KUKA, Xinjiang.